your course home if it's not showing up. All right, but when it does, go ahead and click that yellow join LC session. All right, and I went ahead and delivered that first question. So as soon as you can get in there, read through that first question and calculate the probability that you're being asked to find. It's looking like we're still missing a couple of people in the Learning Catalytics session. So make sure, again, all you got to do is go to your course home tab, click on the yellow join LC session, and you should see that first question when you do that. All right, give me just a little bit more time to get that first one in. All right, so let's talk about this first one. When you are asked to calculate probability, all right, one of the first things you need to think about is total, because you know you're going to need the total to calculate the probability of anything that happens in a particular experiment, right? Because it's always count the event, divide by the total. So in this case, you are told you have a bag containing red marbles, blue marbles, and a green marble, right? So if you're going to talk about probability, All right, what happens when you select a marble from the bag? The first thing you need to ask yourself is, okay, what is my total? In this case, the total number of marbles, right? So in this case, 6 red, 3 blue, and 1 green. That means my total is 10. Okay, I always like to look for the total first because I know I'm going to need it for whatever probability I may be asked to find. Okay, so I have 10 total possibilities. Now, for probability, you're going to count the event and divide that by the total. So you know you're going to be dividing by 10. And the event that we're asked to look at here is that we get a marble that is not blue. All right, watch the wording, be very careful. So all I'm going to do now is say, okay, for the event, how many of these marbles are not blue? How many? 7. Right? You've got 6 of them that are red. You've got 1 that is green. There are 7 that are not blue. That's counting the event. Divide by 10 total, and that gives me a probability of 0.7. All right, 7 out of 10, 0.7, 70%. All those pretty much say the same thing. All right, but the key is to remember you're counting the event and you're dividing by the total. Question, yes?
So yeah, okay, I did get that, but what I was confused on, because it didn't say that, you have to always, like 7 out of 10 would have been wrong. Because I didn't,
Isn't it? It wasn't wrong here. In fact, in this case, I think it took all 3 of them. It took the fraction, the decimal, and the percentage. So 7 out of 10, 0.7, 70%. All those are right.
okay.
But when you're doing like your homework and stuff like that, typically my stat lab is going to ask you to leave it as a decimal. So it would want 0.7 and would count the others wrong. All right. But technically, all those would be
But
correct.
going forward, anytime, unless it's asked, you just leave it
As a decimal.
or the fraction.
Yeah, for our purposes, I would say always default to a decimal because I know in my stat lab, that's usually what it's going to want. And then if it says leave it as a simplified fraction, take that kind of as the exception. Yeah. All right. Okay, so let's try another one. All right, you should see that second one coming through now. All right, so the main thing that I wanted to stress here is that probability is always a number, all right? There should always be a numerical value when you're asked for a probability. And that numerical value should always stay between what two numbers? 0 and 1, right? We know that. We want to make sure when we enter a probability that it does, right? That it makes sense, that it's logical. Now, 0 and 1, those were the extremes. All right, so we said 0 is the probability for something that cannot happen. It's not possible. If something is definitely going to happen, if it's certain to happen, that's the other extreme, and thus it has a probability that's equal to 1. Now, the equivalent percentage is 100%. I saw a couple responses of that, and that's perfectly correct as well. Again, just understand, the decimal and the percentage, both of those are probabilities, but usually you're going to be asked to enter your answer in a specified format. Most of the time it is decimal form. And so in this case, that would be a probability that is equal to 1. So just always remember, because I saw some non-numerical things in here, like some people telling me it is certain, make sure probability is a number. It's always a numerical value. It's always got to stay between 0 and 1. All right, so here comes question 3. Be careful with this one. This is one of those cases where you have more than one event occurring. All right, you're looking at two things happening together, so make sure you take both of those into account. Okay, so in this experiment, again, there are two things happening, right? You're flipping a coin and you're rolling a 10-sided die. Okay, so you have to note that first. So there's one of two ways to handle that. One is to use a tree diagram to identify the sample space, right? Your outcomes would have to look at both the coin and the die. So your outcomes would look like heads 1, heads 2, heads 3, right? Tails 1, tails 2, tails 3. Right? That's one possibility, is to write them out using the sample space. The other possibility is to take them individually and multiply them together to see what happens when they occur in sequence. And I saw about half and half here. About half of you did that. And then about the other half of you gave me 0.5, which tells me you were looking at each event. You just failed to combine them using multiplication, right? Because if we take these one event at a time, right? It says find the probability of getting heads on the coin. So if I just think about the coin, right? Heads is one possible outcome, and there are two total. All right, when I flip a coin, that is the probability that I get heads on the coin. Now, if I just go to the die, it's a 10-sided die, right? So that means there are 10 total outcomes. The event here is that I get an odd number on the die. So how many possibilities are included in that particular event? 5, right? An odd number on the die could be 1, 3, 5, 7, or 9. Counting the event, there's 5 possibilities, dividing that by the total, which is 10. And then again, when you want to pull things together, this happens and then something else happens, then those two things should be multiplied together. All right, so that's going to give me 5 on the top. It's going to give me 20 on the bottom, right? Basically, that's 1/4. And so my probability here should be 0.25. And just a side note, that's the same thing that you would have gotten if you wrote out the sample space. If you wrote out, heads 1, heads 2, heads 3, heads 4, all the way through, your sample space would include 20 different outcomes. And then if you went through and counted how many of them are heads and an odd number, heads 1, heads 3, heads 5, heads 7, heads 9, there would have been 5 of them. So for problems like that, you can really do it either way. You can write out the sample space, right? Sometimes that's a little time consuming depending on how many outcomes you have, but it is always an option. But the shortcut is to say, okay, events happening in sequence, I can multiply. And if I want to do it that way, I take it one event all by itself at a time, and then I multiply those together. Okay, questions there? All right, we'll send this one out, and then I've got to run to my office real quick. My stylus is not working here, so I'm gonna go get my other one. So while you work on that, I'm gonna run and grab that. I'll be right back. Okay. So again, first thing you want to do when you're finding probability is look for the total. You know you're going to have the total. Now, in this case, you were given a data set, you were given a frequency distribution. So what should you do first to determine the total number of outcomes here? Do what now? Add up the number of employees, right? You need a total number of employees in this case. So you're going to take, anytime you have a frequency distribution, you're going to take those frequencies and you're going to add them up. So what did we get for our total number of employees here? Anybody got that handy? If not, 770? All right. So we had 770 total employees. And then the event said find the probability that an employee travels between 10 and 29 miles to work. So you actually have to look at two groups here, right? You had the 10 to 19, the 20 to 29. So to get the number of employees that fell within those two groups, you need to take your 309, your 257, and do what with them? Add them together. And what do we get when we do that? Count the event, divide by the total. Right? Whether you're given data set, whether you're looking at a sample space, whatever it happens to be, that concept for calculating probability is always exactly the same. Count the event, divide by the total. And again, we're typically going to report these as a decimal, rounded to 3 decimal places. And so that would give me a probability of 0.735. All right, and when you went through the homework, it did a really good job of showing you data in a lot of different formats. So you had, frequency distributions, you had histograms, you had pie charts, you had Venn diagrams, you had stem and leaf plots, right? There's lots of different ways that data can be presented, but it's all that same concept. So again, look for the total, get that first, and then all you have to do is count your event and divide by the total. All right. All right, and again, just a quick review. This is more conceptual, right? What probabilities can look like and what they cannot look like. And that's super important to make sure when you're typing in an answer, that is a probability, that it is even a possibility for that. All right, so scan through that list. I just sent them out. Select any of those that could represent the probability of an event. All right, so we said just a few minutes ago, probabilities have to stay between 0 and 1. The equivalent percentages, right, are 0% to 100%. So anything within that range is good. So as I scan through these, right, 0.01, that's a very small chance, but it is a possibility, right? That's between 0 and 1. B is 1.4. Not possible, right? It's got to stay between 0 and 1. And again, that's important if I'm doing my homework or even more so on a test, and I calculate the probability and I get 1.4, I want to stop right there and say, that can't be right, because it's got to stay between 0 and 1. All right, negative 0.4, again, got to stay between 0 and 1. Doesn't make sense to have a negative % chance. 5.75, way too big, right? Got to stay between 0 and 1. Why is 7/5 not a possibility? Right, and the way you know that is the number on top is bigger. So, you can look at it in one of two ways. 7/5 is more than 1, or think about what you're doing. You're counting the event, dividing by the total. Well, the event can't be bigger than the total. And that's another reason why it's got to stay between 0 and 1. All right, 0 and 1 are fine. Those are just the extremes. 15/21, that would be fine. It would stay between 0 and 1. 33%, that's okay, between 0 and 100%. But 115% would not make sense. All right, it's got to stay between 0 and 1. All right, and then let's do one more. And this one is actually based on the fundamental counting principle. This was the very last thing in section 3.1. This is what I posted for you later on. So read through that. This is not a probability that you're calculating. All right, so we don't have to say between 0 and 1. This is a how many. How many possible access codes would there be based on the information that you are given? Remember, when you've got multiple things to consider, the best thing to do is break it down where you can look at one piece at a time. All right, so give you a little hint here. The way that I would set this up is the first thing I would note is, okay, this has 5 digits. That means there are 5 different things that I need to consider and I need to count. So I'm going to lay out 1, 2, 3, 4, 5 different pieces that I need to consider. And then what I'm going to do is I'm going to count the number of possibilities for digit 1, for digit 2, and all the way across. And when we talk about a digit, right, how many possibilities are there for a single digit? There are 10. It can be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay, so break it down. Think about one part of the code at a time. Digit 1, 2, 3, 4, 5. Count the number of possibilities for each one. And then fundamental counting principle says to put those together, we would multiply the number of outcomes. Why not? That doesn't mean it's wrong. And you're going to see that even more so today in 3.4. When you talk about, looking at a total number of possibilities, especially when it comes to things like access codes, and the numbers are generally very large. So don't think you're wrong just because you got a really, really big number, right? Think more based on the concept of what you're doing. All right, so it looks like we've just about got everybody in. And so let's just run through this. All right, so again, when I'm looking at a situation where there are multiple things happening, right, and I want to count the number of possibilities, this is the first thing that I do, right? I lay it out. How many things do I need to look at? And in this case, it was a 5-digit access code, right? So that means I got to figure out the first digit, the second, and all the way across. So I lay it all out, and then that allows me to look at one piece at a time, right? And we already said when we talk about an individual digit, again, we're counting the outcomes. There are 10 total outcomes, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if there were no restrictions on this access code, I would just put 10, 10, 10, 10, 10, right? Each digit has 10 possibilities, but there are a couple of restrictions. So it says the first and the last digits cannot be 0. So for digit number 1, it doesn't have 10 possibilities. It has how many? 9. It can be any of them except for 0. So I'm going to write that down here. 9 possibilities. The middle digits have no restrictions. So they can be anything 0 to 9. And then the same thing as the first for the last, right? The last digit can be anything except 0. And so it would have 9 possibilities as well. And once you break it down, this is all the fundamental counting principle says. It says if you look at it one piece at a time, then you can pull it back together by multiplying the number of individual outcomes, right? So 9 times 9 is 81. We got 3 10s in there. That means there's going to be 81,000 possible access codes. And so when it comes to the fundamental counting principle, we kind of talked about this because we talked about multiplying probabilities, right? Well, this is the same thing. It's just multiplying outcomes versus the entire probability value. So for any situation, when you are asked to count the number of outcomes and you have multiple things occurring, take it one piece at a time, count them individually, and then you can multiply to pull those together and get your total. All right, question. This again was the last thing in 3.1. And so if you didn't know, I posted a video for you there. I think it was Friday before I got it up, but I posted a video for you there. It's still on your announcements page. So you can go in there if you want to see some more details. But essentially, this is all it says, all right, is that you can break things down piece by piece, count them individually, and then multiply to get your total. All right, so because we didn't get to this last part last class, I did push your homework out to the end of the day today. All right, so hopefully you've been able to, complete most of it, but I wanted to make sure we had a chance to at least touch on this. Any other questions from section 3.1? Let me make sure I did fix that due date. Yeah, so you should see your 3.1 homework. Your demonstrate homework is now set to be due tonight versus last night. 3.1, yeah. Normally it would have been due last night, but just because we didn't have a chance to hit quite everything, I pushed that just a little bit. So if there was anything that you were, having trouble with, then you have until tonight to get that completed. All right. So what we're going to look at today, the other section that we cover in chapter 3, are some additional counting principles. So that one we just touched on, that's called the fundamental counting principle. Basically just says, again, you can take pieces individually and then multiply to get their total. In 3.4, we're going to look at 4 additional counting principles, right? More specific counting principles. And we're going to talk about the places where they can be used to count the number of possible outcomes. All right, and these are going to be situations with a large number of possible outcomes, right? Like the 81,000 and even bigger that we just saw. And that's why we're going to need counting principles for these, because these are going to be situations where a sample space, a tree diagram, not feasible, right? It would be huge and it would have thousands or millions of different possibilities. All right, now the two types of experiments that we're going to be looking at here with the counting principles in 3.4 are, number one, when I want to arrange objects in order, and number two, when I want to select objects from a group. All right, those are going to be the two main cases that you see here. Do I want to order things, or do I just want to select and form a subgroup? All right, and we're going to start with ordering. So everything that you see here on this first page, this is dealing with what we call permutations. And a permutation is nothing more than a fancy word for order. All right, anytime you hear the word permutation, you want to think an ordered arrangement of objects. All right, now, when it comes to ordering objects, there are some different ways that I can do that. Sometimes I want to order everything that I have. Sometimes I just want to order some of what I have. And sometimes I might have to deal with objects that are repeating or that are duplicates. Okay. So again, I always think it's easier to start with the example and then go back to kind of talking about what the formula says. So that's what I want us to do here. All right, we're going to come back and hit on each one of these, but I want to start by looking at, okay, when would each one of these be necessary? Okay, so let's go ahead and start with our first example. We have a situation where 8 people are competing in a ski race. Assuming there can be no ties, right? The question here says, notice it's counting, how many different orders are possible? All right, again, anytime I see that order, right, I want to think permutation. All right, an ordered arrangement of objects is called a permutation of those objects. And that's exactly what we're trying to count here. All right, now my basic rule for counting the number of permutations or the number of ordered arrangements says, okay, start with your total number of objects, right? Which we do for probability anyway, right? So in this situation, if I start and say, okay, what are the total number, in this case, of skiers? I'm going to use N to denote that, kind of like a sample space. What would N be in this particular example? How many objects do I have to order here? 8. All right, so in all of these formulas, when you see N, that's all it is, the total number of objects. All right, now the very first formula or rule up there that you're seeing tells you that you can count the number of permutations or ordered arrangements by taking N factorial. N with an exclamation point, that's called N factorial. All right, and N factorial is a product. N factorial says start with N, whatever it is, and multiply every integer between there and 1. So in this case, right, we would need to take 8 factorial. So I would start with 8, and then I would just multiply each integer all the way down until I get to 1. Because essentially all I'm doing here is I'm saying, okay, any of the 8 skiers can be first place. And then anybody can be second place except for the one who was first. And then anybody can be third place except for the first 2, and so on. Okay, but it is a rule, and this is what the first formula, if you will, says. It says the number of different permutations, ordered arrangements, for n total objects is found by taking n factorial. All right, and again, n factorial is always just, start with that number and multiply every integer until you get all the way down to 1. So you can see this is going to be a large number that we're dealing with here, right? 8 factorial, if we go ahead and take that product, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, 8 factorial has a value of 40,320. And again, that might seem incredibly large, but if you really break it down, right, then it makes sense that we're just looking at all the different possibilities for first place, second place, and then we're multiplying because that's what the fundamental counting principle tells me to do. All right, now factorials, they get really big really fast. All right, every time you introduce an additional object, the factorial grows very quickly. And so chances are you have a factorial key somewhere on your calculator. If you at least have a scientific calculator, you should have a factorial key somewhere on it. And so it's a good idea to go ahead and try to find that. All right, so on a basic scientific calculator, chances are you're just going to see this little exclamation, or it might say X with an exclamation, it might say N with an exclamation, might be a second function somewhere. If you have a graphing calculator like the TI-83 or the TI-84, then you're going to have to go under your math and probability menu to find it. You'll hit your math key, you'll go over to PRB, and then you should see the exclamation point there. All right, so just take a minute now, see if you can find it and use that to evaluate the 8 factorial, because we know what it is. That way you can make sure you're getting it correctly. You should just have to type in 8, go find your exclamation point, and then hit enter to evaluate. All right, is everybody able to find it on their calculator? Anybody not find it? It should look like an exclamation point. Let me see. It's either going to be on a key or it might be under like a math menu or a probability menu or something like that. Yep, that's where yours is. So go back to your home screen. All right, let's get back. Okay, type in 8. You want to type in first, then go PRB. And then to the exclamation. Yep, and then enter to evaluate. And that'll be it. Yes, yes. So let's look. Yours is the same as hers. So type in 8. Put that first, yes, and then go PRB exclamation. Yes, that's it. All right, you guys on Zoom, anybody having trouble finding that? It's just going to make things a little easier down the road if you don't have to evaluate every single factorial with a product. Okay, so that's first, right? When you see a situation and you want to take your objects and arrange them in order, and the question is, how many possibilities are there? All you have to do is evaluate n factorial. All right, now let's compare this to the second example, right? And talk about the difference, and then we'll talk about what the rule looks like. In the second example here, we still have 8 objects to consider, right? In this case, we're talking about a list of 8 activities, right? So we would still start with, okay, what is the total? In this case, the total number of activities. And that would be our value of n for this experiment. Now, if it said, in how many ways can the subject arrange all 8 activities? Then your answer would be the same as the previous example. 8 factorial, 40,320. The difference here is it doesn't say in how many ways can they arrange everything. It says we just want a first, a second, and a third activity. So in this particular example, we have 8 total activities, but the number of those activities that we actually want to order is 3. We just want a first, a second, and a third place. When you're not ordering everything, this is typically introduced as a second variable, and it's typically labeled as R. Right? N is the total number of objects. R is the number of those objects that you wish to arrange in order if it's not all of them, which is what happens here. All right, this is a new rule. This is something called the NPR function. All right, looks like this, right? NPR. And chances are you have this on your calculator around the same location that you found the factorial. All right, so in this case, when I just want to order some, right, I would be evaluating the number of permutations from 8 total objects ordered 3 at a time. All right, this is what it looks like. This is just notation, first of all. All right, this is what it looks like when I evaluate 8 total activities where I only want to order 3 of them. All right, now the NPR rule, and again, this is one of those rules that's defined on the first page. Say that again. Good, good. So let me just show you, yes, you do have the button on your calculator, and yes, you're going to use it, but just so that you know where it comes from, all right? Or when you're going through your homework, it's going to start showing you formulas. You want to make sure that you understand what it's referencing. What it does is it takes the total, all n factorial, and it divides out the ones that it doesn't need, all right? N minus r factorial. So in this case, using the formula, right, which says n factorial divided by n minus r factorial, right? N is 8, so I would take 8 factorial, and I would divide that, right? N minus r is 8 minus 3. It's basically the 5 that we don't want would be divided out. Okay, this is using the formula. All right, and so if I go to my calculator and I take 8 factorial, I'm using my exclamation here, divide by 5 factorial, it's going to show me that there are 336 possible ways to arrange a first, a second, and a third activity. All right, but yes, you do have an NPR function somewhere on your calculator, all right, right around where you found the factorial. And so the easier thing for you to do is just to let your calculator evaluate. It's real easy with factorials, especially, to get very tangled up in the work of the formula. And if you're going through the homework and you click on like view an example for this section, it's going to look kind of messy because they're working through the entire thing by hand, and it gets very long and complicated. I don't want you to get tied up in that part. I want you to focus on when do I use each one. So for a situation like this, right, instead of working through all this, once you determine it's NPR, once you know N and you know R, then you're going to take this, you're going to go to your calculator, and you're going to evaluate. All right. And most of the time, yes, you type in N. So like in this case, I would type in 8 in my calculator, go find your NPR, type in 3, and when you enter, that's going to tell you that same thing that the formula did, which is 336 possibilities. Okay, so I'm mainly showing you the formula here. Number 1, so that you know where this number is coming from. But number 2, because you're going to see this reference in the help tools. Right? If you go to view an example or help me solve this, it's going to walk you through using the formula. All right, you don't have to do that. You can use your calculator to evaluate. You just need to focus on knowing when to use NPR. That's when you want to order some of your objects, and then knowing how to input that information into your calculator. All right, questions? Okay, so we've talked about 2 rules so far. All right, we talked about the first one, just the basic n factorial. This is what you use when you want to order all of your objects. Just do an n factorial, like all 8 here. All right, the second thing that we talked about was the NPR function. This is still a permutation, so you're still talking about an ordered arrangement, but this is used when you only want to order some of your objects. All right, and R is the number of objects that you wish to order. All right, there is one more rule that's referenced here, and this is what we call counting distinguishable permutations. This is only going to be necessary when you're looking to order, but you have a situation where objects repeat, you have duplicating objects, you have objects that are of the same type, and those things have to be divided out. All right, they're like duplicate orders, orders that don't look any different or that are not distinguishable, and thus we don't want to count them. All right, so I'm gonna skip ahead just for time. I'll post this third example for you because it's gonna be pretty much like the one before. All right, but I want to skip ahead and look at the fourth example to see this other case. Okay, so we're looking at planning a subdivision. We have 3 different types of homes. We have 1-story, 2-story, and split level. And the question here says, how many ways can the houses be arranged? Okay, so again, we're counting. And arrangement, that's another word for order, right? If you're arranging objects, right, you're determining what order they're going to be in. And so I want to note here that I'm once again counting a number of ordered arrangements. Thus, I'm counting the number of permutations. All right, it's just important to note that to know, is this a case where these rules are even going to work? Now, if I'm going to count the number of ordered arrangements, right, I must have the total. And so I'm going to start with that first. All right, so in this case, we are arranging the houses. So what would N be? Our total number of objects. How many houses do we have to arrange? And 2 split level. So we got 12, right? So look for that total first. All right, I've got 12 total houses that need to be arranged. All right, now from there, I'm going to make sure that I don't need to use one of the other cases. So basically, I ask myself 2 questions. The first thing I ask myself is, do I want to order all, or do I just want to order some? All right, because that's the difference between a factorial and an NPR. All right, this is not an NPR, right, because we are asked to arrange all of the houses. So the second thing I ask myself is, okay, do I have objects that look the same? Do I have objects that repeat? Do I have objects that are of the same type? Or do I have duplicating objects? And the answer to that question here is yes. I have multiple 1-story houses. I have multiple 2-story houses. And I have multiple split level houses, right? I have houses that look the same, all right, that are duplicates. And so when that happens, I write each one as a subgroup, okay? So I'm going to do N1 as my first subgroup, and that's going to represent the 6 1-story houses that I have. I'm going to do this for each group of repeating objects. So I'm going to have an N2 that represents the 4 2-story houses. That's my second subgroup. And then I'm going to have an N3, which represents the 2 split level. When this happens, when you have a total, and then you've got these subgroups that look the same, what you do to count the number of distinguishable permutations is you take n factorial, start with the big picture, And then you divide out the factorial on any of these subgroups where objects look the same. All right, that's what the formula looks like. Plug in numbers in here. I would say, okay, I have 12 total houses to be arranged. So I'm gonna start with 12 factorial. But because I have duplicating objects, I'm gonna divide out each one of those subgroups. So I'm gonna divide out a 6 factorial, a 4 factorial, and a 2 factorial. Now, you can type this into your calculator just like this. You don't have to evaluate each one. You can leave the exclamation points, but make sure you put parentheses around that denominator so that the entire thing is divided out. And for scientific calculators, you may even need to put a multiplication in between the factorials on the bottom, kind of depending on your calculator. All right, so try that here. Try to evaluate that using the exclamation point in your calculator. Type in 12 with the exclamation point, divided by, and then in parentheses, 6 factorial, 4 factorial, and 2 factorial, all enclosed in parentheses. And you should get a total number of distinguishable permutations, right, where nothing repeats, nothing looks the same, at 13,860 when you evaluate that formula using your factorials. There's not a shortcut key for this one, like the NPR, but you can, again, leave everything with the exclamation point and let your calculator evaluate the whole thing in one step. And that, again, is something I want you to remember when you're doing homework. Because again, when you go to your homework for a problem like this, right, it's going to show you the formula, but then it's going to start evaluating all those products. All right, it's going to be 12 and 11 times 10 times 9, and it gets very messy. All right, you don't need to worry about that part. Use the help tools to make sure that you're plugging into the formula correctly and that you're using the correct formula. But once you do that, then you go to your calculator and you use the factorial key or you use the NPR key versus working through all those products. All right, any trouble getting that to evaluate? Okay, so that's what these first 3 rules say. All 3 of them are counting the number of permutations. All right, so first thing, make sure that what you're doing is arranging in order. And then ask yourself which one of these 3 cases you have. If you want to order everything and all the objects are different, just do an n factorial. If you want to order everything, but you have repeating objects, right? You have these little subgroups, then work for distinguishable permutations. And if you want to order objects, but only some of the objects that you have, then you will use an NPR function. Okay, so as you're working through the homework in 3-4, you're going to have to decide which one of these rules is appropriate to use, and that's how you do it. Is it in order? And then am I ordering all different objects? Do I have repeating objects, or am I just ordering some? All right, now there is one other type of experiment where you're going to be counting here, and it is a situation where you are not looking to order, you only want to form subgroups. So it has the N and the R, right? Much like the NPR function that we talked about just a little while ago. But for a combination, N will still represent the total number of objects. But a combination is not looking to order. So in a combination, R simply represents the number of objects that you want to select without considering any ordered arrangements. So it's a situation where you're not interested in counting the orders. You're only interested in counting the groups that are possible. All right, so for example, I'm going to conduct an experiment. I need 4 subjects to be randomly selected from a group of 20. And the question here, what I'm counting, how many different groups are possible? So I look at this and I say, okay, I'm looking to count. I'm going to use one of my counting principles, but I'm only counting the number of groups that are possible. And the order doesn't matter at all. It's not like I'm going to rank them 1, 2, 3, 4. I'm not going to assign them like rank offices, like president, vice president, right? None of that matters here. All I'm looking to see is how many groups are possible. And I'm not going to do any ordering at all. That is a situation where you use a combination to count the number of groups or selections without counting the ordered arrangement. All right, so again, once I determine that NCR is what I should be using, then I would say, okay, I've got 20 total objects, and I want to take them 4 at a time. All right, N is the total number of objects, R is the number of objects that I'm going to select for my group. Now, once again, you've got a formula basically dividing out everything that you don't want. But kind of like I told you with the NPR, rather than getting hung up in the formula, go to your calculator. All right, go to your calculator here, type in 20, find your NCR function, because there's no order here, and then type in the number of objects that you wish to order, or not order, that you wish to select, which in this case is 4. All right, so again, use your calculator, see if you can evaluate this correctly. You should get 4,845 different possible groups of 4 from 20 total. All right, and that NCR function should be right in the same place where you found the factorial and the NPR. All right, the key thing for you to know is that the NCR function should be used when I want to select objects, but I am not interested in the order of those objects in any way.
So is it going to usually say groups over there?
Most of the time, yeah. Most of the time it will state, the main thing to watch out for, like we'll go back, since we have time now, we'll go back to this example just to compare. The main thing to know is that you use NCR anytime you're forming groups, and there's no distinction between ordered arrangements. So like if you compare that to this example that we skipped over here, right? This example looks similar. If I read through it, I would say, okay, we have a club with 38 members. So that's my total. And the question here says, how many different ways can we select, right? So that's pretty much forming a group: a president, a vice president, a treasurer, and a secretary. Right, that's 4 things, right? 4 different positions that need to be filled. So at first glance, I might look at this and say, okay, I'm just selecting, right? I'm just selecting 4 different positions. But if I look at it a little bit more carefully, are these ranked or ordered positions? Yeah, there's a difference between the positions. So in this particular case, it matters who's first, who's second, who's third, who's fourth. Okay, that's the difference. So it might not always, explicitly come out and state order or no order, but there should be something in there that lets you know, is the order important? Does the order matter? Does it make a difference? So in this case, because I have ranked positions, I would not use NCR. I would go back to NPR, because the order of the selections is important. It makes a difference.
You wanna think it's like you can rank it.
Yeah, yeah, because you know, rank, that's kind of just another word for order. So you want to look and see, you know, is there an implied order in there? Are the positions going to be ranked? Is there a difference between them? Any of those cases, the order matters, and you would use NPR. But if you're just going to form a group, say, you know, for an experiment or to do an interview or, you know, things like that, where it doesn't matter who comes first and second and third, that's when you use NCR and that's when you do a combination. All right, and generally speaking, NPR is much larger than NCR. All right, because with an NPR, you're selecting, but then you're also turning around and you're arranging in order. So it's kind of like two things that you're having to count, which is why those values are going to be a lot larger when you're dealing with the NPR function. Okay, now what I want you to do, we haven't finished 3.4. But we have gone through all the new stuff in section 3.4. So I want you to go ahead and get working in the 3.4 homework. You should be able to do probably about 3/4 of the homework. And just stop when you get to questions that start asking you for probability. All right, anything that says how many ways can you do this, you should be able to count that. You should be able to figure out which one is appropriate and then use it to answer the question of how many possibilities are there. All right. I want you to go ahead and do that because I want you to know these pretty well. Because when we come in here on Wednesday and we finish up section 3.4, we're going to talk about how to use those counting principles and apply them to finding the probability, going back to that rule, right? Count the event divided by total. But you need to have a pretty good hold on just the counting rules before we start throwing them in to doing a probability. Okay, so if you need to finish up 3.1, do that first. That's due tonight. But then sometime before class on Wednesday, get in 3.4 and work through, even if it's just practice, right? Work through any of the questions in there that ask you how many ways something can occur. All right, and so we'll pick up with that in class on Wednesday. We'll also go ahead and start chapter 4 at that time as well. So another good reason to go ahead and try to get started on that 3.4 homework.
Did you open up chapter 4 now?
If I didn't, I'll do that right now.